So welcome to lecture 10 of the course Statistical Thermodynamics for Engineers. So this time we are going to do an example problem first. So it's an example problem. Okay, so let's assume that there are 50 independent, indistinguishable particles. There are 3 energy levels. Let's assume the energy level is 0, atom got unit of energy of 0, E, and say 2E. So the degeneracy of the first level is 300. Degeneracy of the second level is 600. And degeneracy of the third energy level is 1200. Okay, so the system temperature, which is written as T, is E by K. So the first step is that if somebody asks you, calculate the partition function. So calculate the partition function. Okay. So the partition function is written as Z, which is summation over J, Gj exponential minus Ej by Kt. Okay, so now this can be written. There are 3 energy levels, as we know. So first one is 300 because the energy is 0. The second one is 600 into exponential minus E by Kt. And the third one is 1200 exponential minus 2E by Kt. And recall the temperature is E by K. So the partition function therefore becomes 300 plus 600 e to the power of 1 plus 1200 e to the power of minus 2. This is, if you do it properly, this will be 683. So now the next question is that find the number of particles, Nj particles, in each energy level. Compute that. Okay. So Nj by N is equal to, as we already know, Gj minus Ej by Kt divided by the total partition function, right? So therefore, N is equal to, as we know, is 50. This is given. So this is 50 into 300 into E to the power of minus 0 divided by 683. So this gives you roughly 22. Okay. So N1 is roughly 22. Okay. So similarly, you can do the other calculations as well. So the last one is say find entropy of such a system, right? So the entropy, as we know, is S, K, Ln. This is in the dilute limit. So this means K summation over J, Nj, Ln, Gj by Nj plus 1. Okay. So here K, as we know, is 1.38 into 10 to the power of minus 23 joules per Kelvin. So S you can calculate from here. Okay, so because you know that different Njs now from the previous example, Gjs are known, so this should be a fairly straightforward piece of calculation which will give you the total value of entropy. So if you do it properly, this will be S is equal to 221 K, where K value is this. So you can find out what will be the total. So this is one example by which you can work out a problem, okay, given the tools that you have learned. Okay. So now let us find out a few other things, that internal energy and entropy in the dilute limit. So as we know, U is equal to E is equal to summation J Nj Ej. Okay, so S will be equal to K beta U plus alpha N minus plus K summation over J Gj ln 1 minus plus exponential minus alpha minus beta Ej. Okay, where alpha, as we know, is minus mu by kt, whereas beta is equal to 1 over t. This is already known, right? So this is the total expression that we have. So now, okay, Nj is equal to N by Z Gj exponential minus Ej by kt. So therefore U will be equal to summation of J, as we know, Nj Ej. So this will be then equal to J, okay, N by Z, that is the partition function, Gj Ej exponential Ej by kt. Okay, so in other words, U is given as N over Z summation over J Gj Ej exponential minus Ej by kt. Okay, so this is U in terms of the partition function, the total number of particles, the degeneracies, the energy level values, and the temperature. So this is the form of U. Now, as we know, dz by dt at constant volume can be written as 1 over kt square summation over J Gj Ej exponential minus Ej by kt. So let's just circle the U so that you remember it. Okay, so now U, therefore, because if you look at the terms, U can therefore be written as nk t square by z into dz by dt at constant v. Z we already know. Z was given as summation over J Gj exponential minus Ej by kt. Okay, so it can also be written as, so your U can further be written as nk t square Z by dt at constant v. All right, so this provides the first explanation of U. So Z is a function of v comma t. So therefore U is a function of v t n. So we know this. So this is how you calculate, if you are given the partition function, this is how you calculate the value of U. Okay, so this is how you calculate the value of the internal energy. Okay, now let us put as S is equal to U by T minus mu N by T minus plus, this is also known, we have done it before, so J Gj ln 1 minus plus exponential mu minus Ej by kt. Okay, now exponential mu minus ej by kt is much less than 1. Okay, so therefore, if that is the case, minus plus k summation j gj ln 1 minus plus exponential mu minus ej by kt, okay, is almost equal to k summation gj exponential mu minus ej by kt. Okay, this is further equal to k gj exponential minus ej by kt e to the power of minus mu by kt, which is equal to k e mu by kt into z is equal to kn. Okay, so therefore s is equal to mu by t plus kn minus mu n by t, or s is equal to u by t plus kn 1 minus mu by kt, or further or, so there are a lot of ors, u by t plus kn into ln z over n plus 1. Okay, so if you introduce u now, then therefore s becomes equal to nk t d ln z by dt v plus ln z over n plus 1. So as we can see, z is the key quantity, okay, which is used to calculate all thermodynamic properties. So z is a very key advantage. So we calculated u, we calculated s. Now we can do some additional properties too. So as you can see that all the properties, so z was a function of what? It was a function of the microstates, right? It was dependent on the degeneracy. It was dependent on the energy values, right? It was dependent also on temperature. So now what we have done is that all these macroscopic properties like u, s, and we will see some more, they are all can be cast in terms of this partition function, molecular partition function. And the molecular partition function was once again dependent on the most probable distribution. So all these factors, you can see the interlinking. So Z is a stat thermal concept, and how we have used it to calculate different macroscopic properties, different macroscopic thermodynamic properties. So for example, mu, okay, can be written as minus kt ln z over n. Z is equal to n minus kt. So this is one. So mu I is equal to du by dni, for example, where you have s v nj not equal to I, right? Okay, similarly, we can also have g, the Gibbs, okay, is equal to minus nkt ln z over n. G is further given as h minus ts. Okay, so h is further written as u plus nkt. Okay, now u, we already found out it is nkt square ln z by dt at constant v, or in other words, H is equal to nkt t dln z by dt at v plus 1. Okay, so as you can see now from this you can cast it right in other. So this is the value of H. So H is also written as U plus PV, or PV is equal to nkt. Okay, because H here can be written as U plus nkt. So this is like the molecular version of the ideal gas. Version of ideal gas. Ideal gas. So this assumes, once again, if you recall, that these are independent and they are indistinguishable. Remember the mistake that Boltzmann made for the Boltzons. Also given ideal gas, if you consider as an ideal gas, then of course what we can write is Cv is equal to du by dt at constant v, and Cp is equal to dH by dt at constant p. So therefore Cv can be written as Nk is the differential T square d ln z divided by dt. Okay, and all these are computed at constant v. So you can find out Cp in the same way. So as we can see, so that is left as a kind of like a homework problem that you can find out Cp in the same way. Okay, now let's do a small practice problem. So again, we assume that n is equal to 50. Okay, this is an example. Now n is equal to 50. Okay, there are three energy levels once again, that's 0, E, and 2E. And this is once again G 300. We are taking the same example. G is equal to 600 and G is equal to 1200. Okay, temperature is given by E by K. Well, our task is to find out U and S. S would be from Z. So solution is U is summation of Nj Ej, sum over n. So this is given as n over z, summation over j, gj ej exponential minus ej by kt. So z is equal to summation gj exponential minus ej by kt, which is equal to 300 plus 600 e to the power of minus 1 plus 1200 e to the power of minus 2 is equal to 683. So U is equal to then 50 by 683. N is 50. Now you plug in the values. So 300 into 0 plus 600 into E into exponential minus 1 plus 1200 into 2e, okay, exponential minus 2. So that is the whole thing. So u becomes equal to, if you plug in all the numbers, is 40e. Similarly, if we go to the next one, you will find that S is equal to u over t plus kn ln z over n plus 1, t is equal to epsilon by k, okay, or S is equal to 40e by k plus k into 50 ln, this is 683 divided by 50 plus 1, okay, so S is equal to 40k plus 50k into ln 683 by 50 plus 1. So S becomes 221K. So this was found out in terms of the partition function. Okay, so thermodynamics, so all thermodynamic properties are normally calculated by assume all thermodynamic properties, dynamic properties are calculated, normally calculated by assuming E naught is equal to 0. So any properties is dependent on the choice of E naught. So Ej, for example, is Ej minus E naught. Okay. So therefore, Z prime, if we define it like that, is J. Just hold on what this means. Exponential minus Ej prime by Kt. Okay, is equal to Z exponential E naught by Kt. So this is how we define Z prime. Okay. Similarly, U can be written as nkt square, as we know already. So this is ln Z prime by delta T V plus E naught divided by Kt square. Okay. So therefore, U minus n E naught is equal to n Kt square d ln Z prime divided by dt at constant V. Okay, so this is like what we called a ground state energy. Okay, so CV, S are not affected by ground state energy, right? By ground state energy. As you can see, they are not affected by ground state energy, but U is. Okay, U is affected. So what we need for calculating any of these quantities is ln Z over n. This is one term. Then ln Z dt constant V square ln Z by dt square at constant V. These are the properties which are basically needed if you want to calculate all the numbers, right? All the thermodynamic properties that are concerned over here. So the idea is now that we know a lot about what these quantities are all about, okay, so the molecular, so we can see common theme is that molecular partition function is needed to determine thermodynamic properties, right? Okay, it is needed for determining the thermodynamic properties. So we need, for example, we need Ej, we need Gj for calculating Z. Okay, which further, once you know these two, you can calculate this, and this further allows you to calculate U, S, H, Cp, Cv, etc., etc. So all macroscopic properties, as we saw, can be calculated from the partition function. Partition function is further determined by the degeneracy and the energy of each energy level. So how do you calculate these two is the fundamental question. Because once these two are calculated, you can calculate the molecular partition function. Once you know the molecular partition function, all thermodynamic properties can be calculated at the macro scale. But the question is how to determine Z, because Z is dependent on Gj and Ej. So who gives you the value of degeneracy and who gives you the value of your energy? So this will require an understanding of quantum mechanics. So this is what we are going to do next. That quantum mechanics is needed to calculate your Ej and Gj. Okay, and this will be further needed to calculate Z. Z will be further needed to calculate U, S, etc., H, and Cp, all the other thermodynamic properties that you require for any calculations as such. So the requirement is now we need to shift gears and go and delve that we know the statistical thermodynamics framework now. We now know how to use statistical thermodynamics to calculate macroscopic properties. We also know how the distributions of particles actually determine the final outcome of the properties. And we know that if you average it over an assembly of particles, you essentially get all the properties that you can hope for. Only thing is that so far we have started that we know EJ, we know GJ. So somebody is providing you with those values. So who that somebody is, that comes from your quantum mechanical calculations per se. So that is what we are going to do in the next lecture. So in this particular lecture, we have covered a lot. We have covered a couple of sample problems, for example. We have also determined how specific quantities can be extracted from the partition function, like internal energy and entropy, especially in the dilute limit, how they can be extracted easily from the partition function and provided that you give the values of these and the degeneracy values, okay? So like that, but we have developed a framework by which we can evaluate all these terms, all these macroscopic properties with ease. Now the point remains that how to calculate, how to go the next step and find out that how these macroscopic properties can be evolved from a quantum mechanical perspective. So you saw how the molecular partition function is cornerstone in these particular calculations, So from the next class onwards, we are going to start looking at quantum mechanics, and we are going to see that how, so far we have done a lot of statistics, a lot of analysis. Now we are going to do something on the quantum mechanics and see that what can be how we can calculate these energy levels and the degeneracies that comes out of it. So Schrodinger's wave equation, etc., will come in very handy. So we end this lecture 10 and we will see you in lecture 11. Thank you.